Hey there! Today, we're going to learn how to move a shape around on a graph. We'll take it nice and slow, step by step, so you can see exactly how it all works.
So, let's just start with this one simple question. Imagine you've got a shape, and you just want to slide it to a new spot. You don't want to make it bigger or smaller or even turn it. How do we do that using math? Now, the official math word for this is transformation. I know, it sounds like a big, complicated word, but honestly, for what we're doing today, all it means is moving a shape. That is it. We're just sliding things around. Okay, let's get into it. We're going to start with the easiest move there is, just shifting a shape straight up or straight down.
Here is our very first rule, and trust me, it's a friendly one. If you want to move a graph up, all you do is add a number to the end of the equation. So if you see a plus sign, just think up.
This picture here shows the idea perfectly. See that original blue line? Well, when we add a number to it, we'll just call it C, the whole shape just kind of floats up and becomes the new red line. Every single point moves up by that exact same amount. And the rule for moving down is probably exactly what you'd guess it is. To move a graph down, you just subtract a number. So if plus means up, well, minus means down. It's as simple as that.
Okay, let's look at a real example. The blue U shape, that's the basic graph. When we change the equation to add a +3 on the end, the whole shape just lifts up 3 spaces. See? It's the exact same shape, just in a higher spot now. Nothing else changed. You're doing great so far, so let's move on to the next part. Now, I do want to give you a little heads up. This next move, moving left and right, it's a little bit tricky. It kind of works the opposite way that your brain thinks it should. And I really want to be clear about this. So many people get a little confused by this at first, and that is completely 100% okay. The important thing is just to see the rule, and once you get it, you'll have it forever. All right, let's look at this. When we see a minus sign, like in x minus 2, our brain wants to think, oh, move left, right? But for these side-to-side moves, you have to think the opposite. A minus sign on the inside with the x actually moves the graph to the right. And this picture shows it perfectly. Look at the blue U shape right in the middle. That's our starting point. Now find the purple one. See how the whole shape just slid 2 spots over to the right? So -2 moved it right too. So if minus moves it to the right, what do you think moves it to the left? Yep, you got it. It's the opposite again. To move a graph to the left, you actually add a number inside there, right next to the x. Let's look at the graph together again. The red shape is the one with the +4. See how it's 4 spots to the left of our original blue one? This shows us the rule is working. +4 means a shift 4 spaces to the left. I know it's tricky, but this picture makes it really clear. Okay, to help this opposite rule really stick in your head, let's think about something from the real world. Sometimes thinking about it a different way can really help. Imagine you're hanging a picture on a wall. If I tell you to move it up, you just lift it. Simple. If I say move it down, you just lower it. That's super direct, just like our up and down math rule. But getting it perfectly straight left or right, that can sometimes feel a little less direct, a little different. Well, the math for left and right is like that too. It just has its own special, kind of opposite rule. You have done an amazing job. So let's put everything we've just learned together in one final summary. This is going to be your guide for all this. This table has everything you need to remember. Just notice the pattern. For UP and down, the number is added or subtracted on the outside of the main function. And for our tricky left and right moves, the number is added or subtracted on the inside, right there next to the x. That's the key difference. And that's really it. If you can remember these 2 main ideas, the easy outside rule for up and down, and that tricky opposite inside rule for left and right, then you now understand the basics of shifting graphs. You can totally do this. So we've learned how to slide a shape all over the place. But take a second to think. What else could we do to a shape on a graph? Could we maybe flip it over? Or even stretch it out? Well, that's what we're going to explore next time. Thanks for learning with me today.
Hey there! Ever looked at a math problem and just thought, wait, that makes no sense at all? Well, today we're going to tackle one of those rules. It's about moving graphs left and right, something called a horizontal shift. And I promise, by the end of this, it's going to be totally clear.
Okay, first things first. I want you to know that it is completely okay if this rule has confused you before. Seriously, it confuses so many people. It's kind of famous for being tricky, so if you've ever felt stuck on it, you're definitely not alone. So here's the secret to getting this right every single time. You have to remember one big idea. For this rule, everything is the opposite of what you think it should be. If you can just get that one concept in your head, believe me, you are already halfway there.
All right, so let's break it down. We're talking about horizontal shifts, right? This is what happens when we add or subtract a number inside the parentheses, right next to the x. That's the key. The action is happening inside with the x.
So here's the rule itself. When you see f of x plus c, so a plus sign inside, the graph actually moves to the left. And when you see f of x minus c with a minus sign inside, the graph moves to the right. I know, it feels completely backwards, but trust me on this, okay? Here's the absolute best way to remember this. Just think of it like it's opposite day. You know, normally on a number line, a minus sign means go left, into the negatives, but not here. In the wild world of horizontal shifts, a minus sign means go right, in the positive direction. And a plus sign? Yep, you guessed it, it means go left, in the negative direction. It's opposite day in math class.
You know, just talking about a rule is one thing, but seeing it actually work is how it really starts to make sense. So let's look at a real example, using a function you've probably seen 100 times, y equals x squared. Okay, so this is our starting point. This nice blue U shape is our basic parabola. F of x equals x squared. See how that bottom point, the vertex, is sitting right there at 0? This is our before picture. This is our home base. Now check out the red graph. This is where it gets interesting. This graph is g of x equals x plus 4 squared. Notice that plus 4 inside the parentheses? So, on opposite day, what does a plus sign tell us to do? It tells us to go left. And there it is. The whole graph just shifted 4 spaces to the left. The vertex is now sitting at -4.
And just to prove it wasn't a fluke, look at the purple graph. This one is f of x equals x minus 2 squared. It's got a minus 2 inside. So where did it go? You got it, 2 spaces to the right, over to positive 2. That minus sign told us to move in the positive direction. See? It's just opposite day.
So after seeing all of that, let's boil it down and make it as simple as possible. If you're going to remember just one single thing from our little chat today, this next part is it. This is the whole key. So here it is, the one thing you need to remember. When the change is inside the parentheses, a plus sign moves the graph left and a minus sign moves the graph right. Let's say it together. Plus is left, minus is right. Once you lock that into your brain, this rule will never ever trick you again. Now, what other math rules have you seen that feel like they're from opposite day?
Have you ever looked at a graph and wondered, how in the world do you flip that thing upside down or sideways? Well, it might look complicated, but the secret is actually just one little symbol, the minus sign. We're about to crack its code, so let's dive right in. First things first, what are we even doing here? You know, the official math term is reflection, but honestly, just think of it as flipping. It's literally like a shape is looking at itself in a mirror, and that line we're flipping it over, that's the mirror, giving us that perfect reversed image. Okay, now this is the one thing you really need to get. It's the master rule for all of this. It all comes down to where you decide to put that minus sign. Is it outside the main function, or is it tucked away inside? That one little decision is the command that tells the shape exactly how to flip. So here's the deal. When you put a minus sign outside the function, like negative f of x, that's a direct order to flip the entire shape upside down, right over the horizontal x-axis. But if you take that same minus sign and stick it inside, right next to the x, like f of negative x, you're giving it a totally different command, flip sideways, with the vertical y-axis acting as the mirror. That's the whole secret. Outside flips down, inside flips sideways. All right, enough talk, right? Let's see this rule actually work. First up, we're going to tackle the upside-down flip. We'll start with a shape I'm sure you've seen before, the classic U shape that you get from the function y equals x squared. It's our starting point, a nice, simple curve that opens upwards. And here's the proof in action. We just take our function and pop a minus sign right out front, making it y equals negative x squared. And check it out. The original U shape immediately flips upside down, right over the x-axis. That is our outside rule working perfectly. Simple as that. Okay, so we've totally mastered the upside-down flip. Now it's time to handle the other half of our secret code, the sideways flip. And just to prove this isn't some one-trick pony, We're going to switch things up and use a totally different shape. Let's try the square root curve. Y equals the square root of x. You know the one. It starts in the middle and just kind of swooshes out to the right. Now watch this. This time, we stick the minus sign inside the function, right under that square root sign. So it becomes y equals root of negative x. And boom! The original curve flips completely sideways, right across the vertical y-axis. Now it's pointing left instead of right. See? It all depended on where we put that minus sign. So there you have it. The secret code is cracked. It's all about location. A minus on the outside flips it down, a minus on the inside flips it sideways. It's a simple little rule that lets you transform pretty much any graph you'll ever see. So now that you know the secret, what are you going to go flip next?
Hey there. So last time we talked all about sliding graphs around, up, down, left, right. But what if we want to do more than just move them? What if we want to actually change their shape? Well, that's exactly what we're diving into today, how to stretch and shrink graphs. And trust me, it's way easier than it sounds. Right, that's the big question. What if you could literally grab a graph and pull it, make it taller, or maybe squish it down and make it shorter? That's what this is all about, and it's surprisingly simple to get it done. So what's the secret sauce here? Well, it all comes down to one simple thing: multiplication. We're going to use just one number, a special multiplier that gives us total control over the shape of our graph. And here it is. The whole magic trick is in this little formula: y equals c times f of x. All we're doing is taking our original function, f of x, and multiplying the whole thing by a number we call c. That one number is going to give us all the power. The best way to think about c is to imagine it's like a controller, maybe a dial or a slider. You get to pick the number for c, and by turning that dial up or down, you decide if the graph gets stretched tall or squished short. You are in complete control. All right, so let's crank that controller up. What happens when we pick a big number for c? Anything bigger than 1. This is how we make our graphs stretch. The rule is super simple. Step 1, pick any number you want, as long as it's bigger than 1. It could be 2, 5, even 100. Step 2, multiply your whole function by that number. And step 3, just watch. The graph stretches straight up, vertically. So check this out. It's like we're grabbing the top of the graph and just pulling it straight up. Every single point on that original line gets yanked upwards, stretching it away from the x-axis. And what's the result? The graph gets taller, and because it's being pulled up, it also looks way skinnier. Okay, so that's what a big number does. But what happens if we turn our controller dial the other way? What if we pick a really small number for c, like a fraction between 0 and 1? The process is pretty much the same, but the result is the total opposite. First, you pick a fraction for c, something like a half or a third or a quarter. Then you multiply by your function, and this time you'll see the graph kind of shrink or get compressed vertically. And here's what that looks like. Instead of pulling the graph up, it's like we're pushing it down from the top. We're squishing it, pressing it down towards the x-axis. This makes the graph a lot shorter, and as a result, it kind of flattens out and looks wider. Okay, enough with the theory, right? Let's see this stuff work in the real world. We're going to take a super common graph, the good old parabola, and we're going to use our new multiplier rule to stretch it and shrink it right here. So here's our starting player, our parent graph. It's the standard regular parabola, f of x equals x squared. Think of this as our before picture. Every point on this curve is about to get a makeover. All right, time to bring in our controller. Let's set c to the number 3. That's definitely bigger than 1. So our new equation is g of x equals 3 times x squared. And look at that. The blue graph gets pulled straight up to become that purple one. Every single y value is now literally 3 times higher than it was before. That's what makes it look so tall and skinny. Now let's flip it and use a fraction. We'll set c to 1/3. So our function becomes h of x equals 1/3 times x squared. And just as we expected, the original parabola gets squished down to create that red one. It's now way shorter and wider, just because every y value is only 1/3 of its original height. So here they are, the whole family together. You've got the original right in the middle, then you have the tall, skinny one we made by multiplying by 3, and then the short, wide one we got from multiplying by 1/3. 3 totally different shapes, all controlled by that one little number we put in front. So, if you remember anything, remember this. A big number, anything greater than 1, pulls the graph up, making it tall. A small fraction, between 0 and 1, pushes the graph down, making it short. And remember, we're only changing the height, the y values. Most importantly, you are the one in control of the final shape.
So you now have this awesome new tool in your math toolkit. You don't just have to move graphs around anymore. You can fundamentally change their shape. So the real question is, what are you going to do with this new power? What other kinds of shapes can you dream up and control now?
All right, welcome. Today, we are going to tackle one of the trickiest concepts in algebra, horizontal graph transformations. Stretching and shrinking a graph from side to side. And if you've ever felt like this whole topic just works backwards, well, you're not alone. Let's dig into exactly why that is. So let's just get this out of the way right now. This stuff is weird. It feels backwards. Honestly, your brain is going to tell you that multiplying x by 2 should make a graph bigger or wider. And that's a totally normal thing to think. It's a classic stumbling block. But if you stick with me, we're going to unravel why our intuition gets completely flipped on its head here. So this is it. This is the big question we're here to answer. Why on earth does f of 2x give you a graph that looks all compressed and squished horizontally? And why does something like f of 1/2 x give you a graph that's all stretched out? It seems to go against everything we know, but trust me, the answer is actually really cool once you see it. Okay, so before we get into the why it works, let's just establish the what. What is the actual rule? Well, here it is, straight from the textbook. It basically says that to graph y equals f of cx, you take your original graph and you either shrink it or stretch it horizontally by a factor of 1 over c. Let's break that down into plain English. This is the backwards rule in a nutshell. If that number you're multiplying by, c, is bigger than 1, like the 2 in f of 2x, you actually shrink the graph, and you shrink it by the reciprocal, so by a factor of 1/2. But if c is a fraction between 0 and 1, like the 1/2 in f of 1/2 x, you do the opposite. You stretch the graph by its reciprocal, which is 2. So the rule is always the same. You're just doing the reciprocal of whatever that number is on the inside.
All right, rules are one thing, but seeing is believing, right? To really get this, we need to see it in action. So we're going to use this really simple, clear example from the text called the sawtooth graph.
So here's our starting point. This is our plain old y equals f of x. It's just a simple, repeating zigzag. Take a look at its rhythm, right? It hits a peak at x equals 0.5, it crosses the axis at x equals 1, bottoms out at 1.5, and just keeps going. This nice, steady pattern is what we're about to mess with. And boom, here's our first transformation. On the left, you've got the original. On the right, that's y equals f of 2x. Just look at what happened. The whole pattern is squished. It's happening twice as fast now. That peak that used to be at 0.5, it's now at 0.25. The point where it crossed the axis at x equals 1, it's now happening at x equals 0.5. The whole graph has been shrunk horizontally by a factor of 1/2, just like the rule said it would.
So, why? Why does this happen? This quote right here is the key. In our original graph, f of x, to get the y value at f of 1, you just plug in x equals 1. Simple. But now in our new function, f of 2x, what x value do you have to plug in to get that exact same y value? Well, you only have to plug in 0.5, because that 0.5 gets doubled to 1 before it even enters the function. You're getting to the same y values with smaller x values, and that's why the graph has to shrink to keep up. Now let's look at it the other way, stretching. On the right, we have y equals f of 1/2 x. See how the zigzags are all pulled apart and wider? The peak that used to be at x equals 0.5 is now way out at x equals 1. And the logic is exactly the same, just in reverse. To get the y value that the original graph had at f of 1, you now have to plug in x equals 2, because that 2 gets cut in half to become 1. You need bigger x values to get to the same destination, which stretches the whole graph out. Okay, we have seen the rule, we have seen the visual proof. Now let's put it all together and get to that aha moment. This is the core idea that is going to make this whole thing finally click into place for good. Here it is. This is the single most important thing to understand about all of this. Horizontal changes, whether it's shifting, stretching, or shrinking, they all feel backwards because the math happens to the input. It happens to the x value before it gets sent into the function machine. The function itself has no idea what's going on. It's just getting a pre-cooked number. Let's just walk through it one more time with f of 2x. So you pick an x value, let's say x equals 3. The very first thing that happens is that 3 gets doubled, and it becomes 6.
Then, and only then, does that 6 get plugged into the function f. So the y value that the original graph made way out at x equals 6 is now being made at x equals 3. And for that to happen for every single point, the entire graph has to squish inward to compensate. So maybe a better way to think about this is that a horizontal transformation isn't really changing the graph directly. What it's actually doing is changing the input before it goes into the function. And the graph is just the result. It's the visual compensation that has to happen to maintain that same relationship between inputs and outputs that the original function f had.
So there you have it. You get it now. You understand the backwards world of the horizontal axis, and you know that changes inside the parentheses mess with the input. The question to leave you with is this. What happens when you start mixing these things together? How would you handle graphing something like, say, y equals f of 1/2 x plus 3? That right there is your next step in becoming a master of functions.
All right, welcome. Think of me as your coach for the next few minutes. We're going to come up with the ultimate game plan for graphing some of those functions that look, well, a little tricky. By the end of this, you're going to have a step-by-step playbook that just works. Every time.
You've been there, right? You're staring at some function, you see a minus sign here, a number there, parentheses, and your head just starts spinning. Where do you even begin? Do you shift it left first? Up? Do you flip it over? It feels like you're totally lost in a maze.
Well, check this out. This is the idea that's going to change everything for you. You know PEMDAS for regular math, right? It's that order of operations that brings calm to the chaos. So what if I told you there's a PEMDAS, but for graphing? A clear, set order that takes all the guesswork out of the equation.
Okay, let's get right into this game plan. I call it the 3-step rule, and honestly, it's about to become your new best friend when it comes to graphing functions.
Here it is. Looks simple, yeah? But trust me, the order is everything. First, you deal with anything moving the graph left or right. That's your horizontal stuff. Second, you handle anything that changes the shape, stretches, shrinks, flips. And last, the very last thing you do is move the graph up or down. So remember, horizontal, shape, vertical. Let that sink.
All right, enough with the theory. Talk is cheap. Let's see how this playbook works in a real game. We're going to do a play-by-play breakdown of an actual problem straight from our source material. And here's our challenger. Y equals 1 minus 2 times the quantity x minus 3 all squared. Now our game plan starts with knowing our basic team player, which is the parent function y equals x squared. You know, that classic U-shaped parabola. That's our starting point.
Okay, game on. Step 1 of the playbook says we handle horizontal shifts first. So, where do we look? We look inside the parentheses. Anything happening directly to that x is our first move. And here's the key play. We see x minus 3. Now, your brain might scream, move it left by 3, but hold on. In the world of horizontal shifts, it's the opposite of what you'd think. That minus 3 actually tells us to shift the whole parabola to the right by 3 units. So we just pick it up and slide it over. Boom. First step.
Okay, horizontal position is locked. Now for step 2. The shape changers. We're looking for any number that's multiplying our parentheses. And in our function, we've got that big -2 sitting right out front. This little guy is actually doing 2 jobs at once.
And this shows that 2-part action perfectly. The negative sign, that's our reflection. It literally flips the entire parabola upside down, right over the x-axis. Then, the 2 handles the vertical stretch. It's like it grabs the ends of that flipped parabola and just pulls, making it look narrower, steeper. The shape is now officially set. And here we are, the final play in our book. The graph is in the right horizontal spot. Its shape is correctly flipped and stretched. The only thing left to do is our final transformation, the vertical shift.
You see that +1 hanging out at the very beginning of the equation? We save that for the very end. That's our signal. We take the entire graph we've just built and we just lift the whole thing straight up by 1 unit. And just like that, that's our final graph, right where it belongs.
And look, this isn't just some clever trick I made up. The source material itself confirms this. It literally says the upward shift must be performed last. It's a rule that's baked into the math itself, just like PEMDAS. You always multiply before you add, right? Well, here, you always stretch and reflect before you do that final vertical shift. So let's wrap this up.
We went through the whole play-by-play, so what's the one thing, the absolute golden rule, that you need to take away from all this?
This is it. This is your golden rule. That confusing maze of graphing actually has a map. And that map is the order of operations. Horizontal shifts first, stretches and reflections second, vertical shifts last. Stick to the game plan, follow those steps in that exact order, and I promise you will never get lost graphing a function again.
You know, we see symmetry all over the place. In art, in nature, you name it. But what about in a math equation? Today, we're going to dive into the really elegant, kind of hidden symmetry of functions. And trust me, it's way more visual than you might think. So, can a math equation actually be symmetrical? The answer is a huge yes. And getting how this works isn't just a neat trick, it's a really powerful tool in math. It all comes down to the shape a function makes when you graph it. Okay, first up, we've got what are called even functions. But, forget the technical term for a minute. The absolute best way to get these is with a simple visual I like to call the mirror test. So what does that even mean? Well, it means if you could take the graph on the paper and fold it right down the middle, smack dab on that vertical y-axis, the two halves would line up perfectly, a perfect reflection. Let's take a look at a classic, the parabola, f of x equals x squared. See that? See how the y-axis acts like a perfect mirror running right down the center? The curve on the left is the exact mirror image of the curve on the right. That, right there, is the signature look of an even function.
All right, so even functions have that cool mirror symmetry. Now let's check out another type, odd functions. And for these, we're going to use a totally different visual trick, one I call the spin test. Okay, so instead of folding, I want you to imagine putting a pin right in the dead center of the graph, at the origin, that point 0, 0. If you could spin the entire graph 180 degrees, just a perfect half turn, and it lands exactly on top of where it started, well, then you've got yourself an odd function.
Let's try this spin test out with the function f of x equals x cubed. Picture grabbing that curve in the top right and rotating it 180 degrees around the center. Where's it going to land? Bam! Perfectly on top of the curve in the bottom left. That's what we mean by origin symmetry. And here they are, side by side, so you can really see it. On the left, our even function, x squared, with its perfect mirror symmetry. And on the right, the odd function, x cubed, with its 180 degrees spin symmetry. Two totally different, but, equally cool types of balance. So, seeing the symmetry on a graph is one thing. It's pretty intuitive, right? But what happens if you don't have the graph? How can you be 100% sure just by staring at the equation itself?
That's where algebra gives us a simple, really powerful test. It's like a quick proof that nails it every single time. No graph needed.
The whole test really just boils down to one simple move. You take your function, f of x, and you replace every single x with a negative x. For an even function, you're going to get the exact same original function back, no changes. For an odd function, you're going to get the exact negative of the original function. Okay, let's test our mirror function, x squared. We replace x with negative x, so we get negative x squared. And what happens when you square a negative? Right, it becomes positive. So it simplifies right back to x squared. We ended up with the exact same function we started with. So since f of negative x equals f of x, we've just proven it's even. Now for our spin function, x cubed. We plug in negative x, so we have negative x cubed. A negative number cubed stays negative. So this simplifies to negative x cubed. And hey, look at that. That's the exact negative of our original function. Since f of negative x equals negative f of x, we've proven it's an odd function. See? Simple as that.
So let's lock this in, the key takeaways. Even functions, they pass the mirror test. Odd functions, they pass the spin test. And the algebraic proof? Just plug in a negative x. If you get the same function back, it's even. If you get the negative of the function back, it's odd.
Which, of course, leaves us with one last really important question. What about all those other functions, the ones that aren't a perfect mirror and don't have a perfect spin? What if they fail both tests? Well, the truth is, most functions are in that boat. We simply call them neither. It's a good little reminder that while symmetry is beautiful, it's also a special property. It's not the default.